Hi, okay. My name is Mary Convery, and I'm going to talk about evolution of the Fermilab accelerator complex. So I'll start by talking about the status of the complex, which Young-Key already touched on a little bit. I'll talk about the transition to the PIP2 LBNF Dune era, and then I'll describe the accelerator complex evolution program, which has three parts: accelerator infrastructure readiness, PIP2 integration, and then main injector ramp and targetry, which is for going to higher beam power, and then summarize. So just to remind everyone, for MALAB Accelerator Complex, so currently we have a LINAC that accelerates beam up to 400 MeV, where it's transferred to the booster for acceleration to 8 GeV. In the near future, we'll have the new PIP2 superconducting RF LINAC with a new transfer line to connect into the booster. And then the HF beam can serve the short baseline neutrino program through BNB, the booster neutrino beam lines. It can go into the recycler where it's rebunched and sent to the MU on campus, previously for G-2 and soon for MU to E. And then it can be accelerated to 120 GeV in the main injector for our high energy neutrino experiments, such as NOVA. And in the future, we'll have a new beam line for 120 GeV beam to produce neutrinos for Dune. And then we also have the test beam facility, which takes 120 GeV beam for users. So as Young-Key mentioned, we had a record year of running for the booster neutrino beam in FY25 with our best yearly protons on target and a high uptime. We continue sending beam to the booster neutrino beam for the SBND and Icarus experiments this year and next year, and we're doing well on our beam delivery so far this year. We're also commissioning the beam for MU to E and making good progress on that. We have an irradiation test area off the LINAC, which is operational and supporting users. And then due to the transformer fire that Young-Key mentioned, the NUMI and test beam are currently down, but they'll resume operations hopefully in September when we receive new bushings for some of the transformers. We had some other issues around the same time frame with some corroded heat exchangers that we use for cooling water for the main injector, and those have been repaired. But as impacts of deferred maintenance and end-of-life infrastructure became critical in 2024, the lab recognized this and launched the Accelerator Infrastructure Readiness Program, which I'll talk more about in a few minutes. So first of all, for the timeline for the transition to the PIP2 and LBNF era, so we're currently commissioning MU to E, operating the BNB experiments, and we hope to have a short run for the test beam in September after the transformers are operational, and then NUMI operations can occur on the similar time frame. It could go a little longer possibly if we have approved experiments to run during that time. The switchyard test beam will shut down in December of 26 because for the PIP2 construction. So the PIP2 construction for the beam transfer line that connects the new, so the LINAC construction is already making really good progress. The transfer line construction will begin here. And then we'll be commissioning beam in the LINAC. So then we shut off everything in January of 28 to connect the booster, the PIP2 beam line into the booster and to connect the LBNF beam line into the main injector. And booster will come up and start commissioning beam while LBNF continues its work. And then eventually on this current schedule, the beamline installation for LBNF will be complete in 2031 and we'll start commissioning there. So after this long shutdown for connecting the new projects into the existing complex, we will no longer operate the current LINAC and the associated irradiation test area. We will no longer be able to operate beam to NUMI, which currently services NOVA and the Dune 2x2. The future of the Switchyard 120 test beam program is still to be determined. We had a task force which has considered various options for that and sent those to lab management. Booster commissioning with beam from the PIP2 LINAC uses the booster neutrino beam, which allows an experimental program there if approved. We will be operating beam to the MUTA-E experiment, and then we'll be operating the LBNF beam to Dune. This is a timeline for ramping up to beam to Dune. So once PIP2 installation is complete, we'll start up and commission beam and the booster, start working on increasing intensity, and then reach the point where we can send beam also to the main injector and recycler for commissioning there. As I mentioned, when we want to commission high intensity beam in the booster prior to when LBNF is ready to receive it, we will send beam to B&B if as a beam dump if there's no user, but if there's a user program, we can support that. And at the same time, we'll be sending beam to the MUTA-E experiment. We'll commission slip stacking in the main injector at low intensity limited pulses. And then when LBNF construction is complete, we'll establish beam there, do our beam-based alignment, and then work on increasing beam power for Dune. This shows a relatively conservative timeline for increasing beam power to Dune. It's based on our experience when we increased the beam power from 400 GeV up to 700 GeV. And so in that sense, it's a realistic time frame, but of course we will go faster if we're able to. As far as long-term planning for reliability, the PIP2 project, which has been in the works for quite some time now, replaces the 60-year-old LINAC with a new accelerator. We have the Acorn project, which will modernize our accelerator controls system, replacing our 1980s era ACNET with EPIX, which is a standard control system for accelerators, and replace obsolete components such as our KMAX systems. For the booster, we had the original proton improvement plan in the 2010s, which worked on booster reliability for 15 hertz operations. With PIP2, we'll move to 20 hertz operations, and we've had a task force that was formed in 2020 to look at what studies we would need and what improvements we would need for operation of the booster with the PIP2 LINAC. Then we've had this accelerator complex evolution program, which was presented to the P5 committee in 2023. This includes reliability, main injector ramp and targetry to reach 2 megawatts without a new booster, and then an eventual booster replacement, which P5 deferred. So main injector will be more than 30 years old when LBNF turns on, and its reliability has been considered in multiple workshops with a comprehensive look at risks in this 2024 AD preparation for Dune PIP2 era workshop. And so we gathered quite a bit of useful information on what systems we need to upgrade from that workshop. And then the Accelerator Infrastructure Readiness Task Force was charged in FY25 with identifying infrastructure required to support accelerator operations in support of LBNF Dune. As I said, the Transformer fire sort of brought this to the forefront. And then, as I also mentioned, Fermilab has charged a task force with looking at different options for the future of the test beam, which are independent of ACE, which is ACE's, the Accelerator Complex Evolution Program is focused on beam to Dune and excludes the test beam in the MU on campus. So the Accelerator Complex Evolution Program has three main pieces. It's also connected to the Acorn project, which is modernized on our control system. The Accelerator Infrastructure Readiness Program looks at infrastructure needed to keep the complex running, and the highest priority items need to be addressed before LBNF operations. It's a coordinated project between the Accelerator Division and our Infrastructure Services Division. Then we have PIP2 integration, which covers scope that's needed for operations in the PIP2 era, but that scope is not required in the PIP2 project to be successful. And again, the highest priority items here need to be addressed before PIP2 operations. And then we have the main injector ramp and targetry, sometimes called ACE-MERT. This looks at developing a 2 megawatt capable target and increasing the beam power by shortening the main injector cycle time rather than increasing the proton intensity. And so this is looking at moving beyond 1.2 megawatts that Dune is designed, that the first stage of Dune is designed for. So I'll start by talking about the Infrastructure Readiness Program. Uh, this, as I says, originally there was a task force put together consisting of Accelerator Directorate, Infrastructure Services Division, and then personnel from the various projects that identified end-of-life infrastructure and ranked needs for replacement. We received quite a bit of funding for to work on some of this past year, um, which we have done. We've spent that money. $5 million of that went towards a new transformer, and then we've done a lot of other good work with that. And we got additional money to repair the degraded duct bank that was uncovered during PIP2 construction that Young Key also mentioned. So we've developed a plan for the programmatic infrastructure that's covered by the accelerator operations funding. We assumed a similar amount of money per year that we received last year, and that amount of funding would allow us to address the highest priority items before LBNF is operational. We did, because of other needs that we have in PIP2 integration and the turn on of the PIP2 cryo plant, which uses more electrical power, we did reduce the funding for air from this 7.5 million a little bit in this current year to start ramping up on some of that other work. Outside of the accelerator operations funding, we've developed a request for general plant projects and increased lab indirect funding, and this group has a regular communication with our lab management. We have a planning schedule here, again, with a funding level timeline of roughly $7.5 million a year. And you can see the work that we accomplished in FY25. We repaired the heat exchangers. We bought a transformer. We've rerouting some systems for the PIP2 construction, a new air conditioning unit for our computer room, the duct bank repairs, and then started engineering works for some of these future jobs that we have planned. You can see some of this, the staging of activities incorporates many things. Some of the things can only be done during the long shutdown. Some things are long lead items, and so we want to purchase those sooner than later, and looking for when we would want to actually install the items. We could complete more activities if we had more funding available, but this, we believe, does cover the bare minimum to meet accelerator functionality for June. Okay, so then the next piece of the ACE program is PIP2 integration. The PIP2 project scope meets its key performance parameters, but they don't include everything that's needed for long-term operations, and so that's what this program looks at. We've been planning for this for many years, and the interfaces have been maturing as PIP2 design progresses. And I'll cover a few examples coming up here, including flat injection into booster, a buncher in the beam transport line, and instrumentation at 20 Hertz. So the current LINAC, the PIP2 LINAC has a much smaller current compared to our existing LINAC. And so the injection time, you inject more turns around the booster to collect enough beam in the booster to then send to the main injector. It's not really a problem, except that our gradient magnet field is designed for a short injection time, and then we accelerate the beam. For the longer injection time for PIP2, we need to sort of flatten out this field in the magnets while we're injecting. And so we can apply a field in our corrector magnets to sort of flatten this out. We performed studies last June with the goal to establish a 400 microsecond long flat bottom during beam injection, characterize this with beam position monitors, capture the beam and accelerate it to 8 GeV. This was successful, and we've implemented this in routine operations after that. And then we're currently developing strategy for operations with the PIP2 LINAC, which actually needs an 800 microsecond long flat region. And this will require some corrector magnet power supply upgrades. Booster injection also requires a certain size momentum spread. And currently the design gives us a larger momentum spread than what we will need when we go to high beam power. And so we've designed a buncher, an RF buncher system in the beam transfer line, which can help us reach this momentum spread and also decrease the energy scatter of the beam. And you can see here a schematic for these RF cavities, which will fit into the planned beam transfer line that PIP2 is building. And then the final thing I wanted to mention from PIP2 integration is instrumentation at 20 hertz. We have the complex has been operating at 15 hertz, and some of our readout electronics is not capable of operating at 20 hertz. And so we currently have an accelerator improvement project, which is upgrading the beam profile monitors. We have a prototype crate installed, and we've been testing that with beam. We have good results coming out of that. And then once we have this working, we plan to use the same design to upgrade all of our other BPM and beam loss monitor systems in the complex. So this is a possible funding plan to complete scope in time for LBNF turn on. We're revisiting priorities and timing needs of some of these. As I said, the buncher, for example, is only needed when you get up to 1.2 megawatt intensities, and so this can probably be pushed out a little bit. So we're continuing to refine this. It is a rather large increase on top of our existing budget, and so we need to be mindful of that. And then also some of our scope that's needed for PIP2 integration, but is infrastructure, such as our gallery cooling and our cooling water in the booster that will be needed for operation at 20 hertz. For operation at 20 hertz, that will be covered by the AIR program. And then the final piece is the main injector ramp and targetry. We conducted an alternatives analysis for increasing the beam power versus via a shorter cycle time. So in order to shorten the beam cycle time, to basically accelerate the beam faster, we need to modify our power supply system and our RF system. So we've conducted an alternatives analysis where we asked the teams to look at technical performance and reliability, schedule, and then the cost of implementation, maintenance, and operations. So for RF, they looked at adding additional RF stations, replacing the existing cavities with a new design, and also implementing tunable superconducting RF. For the power supplies, the options are basically adding additional power supplies or replacing the existing supplies with new higher voltage power supplies. And we told the team that although a cycle time of 0.7 seconds is the goal, if there is some intermediate point between what we can do now and that goal, where the cost benefit is significantly higher, to look at that as well. So for RF, it looks like replacing a subset of our RF cavities with a new design is a promising solution, and we're continuing studies on this. For power supplies, if we simply add more power supplies, we will also need to construct new service buildings, and so that can be expensive. And so it looks like a new design that will allow us to add voltage without expanding our buildings would be preferable there. As far as the targetry, there's no point in going to 2 megawatts if you don't have a target that can take that. The target that's being installed by the LBNF project is designed for 1.2 megawatts and is unlikely to be suitable for higher beam power. We've been conducting high power target R&D to find suitable materials. You can see here how that cycle kind of goes as they test new materials, and if that doesn't work, then you go back and you try a different material. And then we also have development for basically seeing how far our existing targets and horns can go and learning from that. I wanted to show one slide on workforce opportunities and challenges. So this looks at various types of labor, such as mechanical drafters, mechanical engineers, electrical engineers, and technicians, so forth. So some of the features of this are, you can see this is the mechanical engineers here. So the various lines, the various colors are different types of, blue is operations, orange is LBNF, green is PIP2. And so that's how much we need of these people. And then the pink line kind of shows how many of those people we currently have. And you can see that as the project design and installation completes, those people are no longer busy at working on projects, which gives them some availability to work on the Accelerator Complex Evolution program. Another feature that you can see here for electronics technicians, for example, the pink line is how many we have. And this up here is how many we need. We do continue to have difficulty hiring qualified power systems engineers and technicians. So if anybody is from universities that train these types of people, please give us a shout out. So to summarize, identification and prioritization of modernization of technical systems was formalized in the 2019 Detector and Accelerator Modernization Plan, and we've been executing upgrades as budget allows. Accelerator Operations has been planning since 2020 how to cover scope needed for operations in the PIP2 LBNF era that's not covered by the projects. The Accelerator Complex Evolution Plan was developed and presented to P5 in 2023 and has been adjusted based on the recommendations from that. And impacts of deferred maintenance and end-of-life infrastructure became critical last year, and we're planning and executing the Accelerator Infrastructure Readiness Program to address this. Thank you.
Thanks very much, Mary. We have a few questions in the live chat from Sarah Eno. Regarding the future of the test beam, are the user communities being consulted by management on this? And can you talk more about the manpower problem? Is it severe enough that it will necessarily cause delays? Are there open positions now?
Okay, so let me address the second question first. I believe we do have open positions now. We are prioritizing the projects, and so if anything, we try to limit the impacts to operations. And you can see that we're operating pretty well, so I'm not anticipating big delays to the projects, but it is at this point anyway, but it is a concern. As far as the test beam, if anyone from lab management is on, they're welcome to speak up. I believe that the task force delivered its report to lab management, and then I don't know what the process is after that.
Okay, we have a question from Shekhar Mishra. How much of AIR PIP2 integration and main injector ramp and targetry funding are approved and or in DOE funding profile for Fermilab?
So my understanding is that the $7.5 million a year that we assumed for the accelerator infrastructure, that seems like that the DOE indicated that they, my understanding is that will continue, and so that's sort of approved as much as you can approve anything that's on a year-by-year basis. The PIP2 integration, I believe, is above and beyond our existing budget, and I don't know that funding is readily available, so that could be an issue. We will, try to cover that as much as we can in whatever budget we have. And then the main injector ramp and targetry, also I believe is not currently in the budget, but does not become urgent until after that's to get to the next level. So first we got to get to 1.2 megawatts, and then we'll worry about the next step there.
Thank you, Mary. I don't see any other questions in the live chat. Does anyone have a question for the chat, or does anyone want to raise a hand? If not, then thanks a lot, Mary. And
thank you.
We'll go on to the next talk by